Okay, let's get started. Any questions from previous lecture so far? So the plan today is to finish fermion and move to vector field. Okay, and then we're gonna spend maybe 2-3 lectures. Yeah, 2 to 3 lectures on the vector field, and then after that, the rest 2 months or so, we're gonna talk about renormalizations and stuff. Okay, so that's the plan. Okay. Good. So last time, so we start talking about Wick theorem and Feynman diagrams, Feynman rules for the fermions, right? So we talked about that. So quickly, so we define a contraction for fermion field. For instance, this, as usual, as a difference between time ordering and then normal ordering. And you remember that both for the time and the normal ordering, so let me just say order either time or normal ordering. If I have a fermion field 1 to j, we have to devise a slightly new rule for the fermion ordering, because now we have to have this factor, and then if I want to order this guy according to j1 to jn, for instance. So either this ordering is according to time ordering if I'm talking about time, or it will be normal ordering if I have to do the normal ordering. But then this means that when I bring this sequence of field into whatever form I have to, if I make p permutations, I have to have that. Okay? So then we had Lorentz invariant notion of time and normal ordering and so on. So we talked about last time. And then with that, now obviously now you can go on and then do usual way of doing scattering process. So there's the in state and out state, which as we know, in terms of plane wave basis, we can write it as S operator. Then S operator, according to the Dyson's formula, we have time order exponential of minus infinity to the infinity equal x, and then interaction picture interacting Hamiltonian, right? And then we can do the order by order expansion and then study perturbation theory for any given process that we're interested in. So that's what we set up. And then we look at for instance, process. So we consider the case where we had a Lagrangian, where I had 3, first of all, scalar with some mass, which I put U square. And then we have a Dirac fermion with m versus mu. And then we wrote down a interaction between this and the scalar length. So for instance, I said that let's call this guy as a particle, which is n, and then there's an antiparticle, which I call n bar. So nucleon, antinucleon, and then there's a meson, for instance, phi. So last time we look at the process where, so the example process we looked at was nucleon colliding with a meson, or pi, if you like, and then going to nucleon plus scalar phi. And then the relevant diagram, if you actually expand this with that interaction term here, and then you can expand, you get, for instance, one of these diagrams. So there's a phi coming in with the momentum in, and the n with the flu going in with the momentum, and the phi coming out with the momentum, and then there's a charge flu, there's n coming out, right? For each vertex, we had a minus ig times gamma as the Feynman rules, and then we say that, okay, you have to reverse the order of the charge flu, and then since I'm talking about nucleon to the nucleon, and remembering that psi has, if you like, annihilation operator with u, which is for the particle, so then we put n there to just emphasize n. And then there was a creation operator for the v, which is n bar. So, and then reversing the charge order, we say, okay, this amplitude in terms of matrix element A, I reverse, and then I read out u bar first. So first I have ig squared, and I have 2 vertices. And then u bar, if I assign momentum P, Q, Q prime, D prime. So I have U bar, U P prime. And then I hit the first vertex here. So let me draw better. I have gamma. And then I have a fermion propagator. In this case, that momenta is Q plus P. So we have P plus Q M plus I slash. That's the propagator. I hit another vertex, which is gamma, and then U. So that was the amplitude to be read out. Okay, so I think I talked about that much. So today, basically, we will finish up this part of the discussion and move on. Good. So that's good. You can also do a similar computation if you replace this with an n bar n bar. In that case, basically the same diagram. Instead of time going that direction, now you have to read everything backwards. So now this is the initial state because now this, so something going in the momentum, but going against the charge flow, that's antinuclear. Okay, right? So phi antinuclear going in, phi antinuclear coming out. So basically, same diagram. We have to read this diagram backward in time, basically, compared to this process. So you can also try to write down amplitude, which I will leave you as an exercise. But I want to talk about one thing though, before I switch off to something else. Okay, so what I want to talk about is a property. So did I write down full Feynman rules before or not? Did I? I don't think I did. So let me do it just for the sake of it. So for instance, if I have a scalar, which you note that I'm writing as this, and then if I specify momentum direction like so, then I have to have propagator in momentum space. So I'm writing everything in the momentum space. Remember, Feynman diagram and the Feynman rules are for amplitude. It's for computing amplitude. And amplitude is a function of external momentum. Okay? If you happen to remember, before we developed the Feynman amplitude and Feynman rules, we also talked about weak diagrams. The weak diagram were diagrammatic representation of this expansion, which were operators, not the C, not function. Feynman amplitude is a function of momentum, external momentum. And then this thing, if you expand, this is an operator, has a lot of operators. And there was another diagrammatic representation for operators. Okay, it's good to understand. So now, eventually, we want to compute that sandwich between two in-state and out-state, right? Once you do that, this turns into a function of external momenta. And then we notice that instead of keeping track of space, because we are going to anyway integrate over the entire space of the vertices, we now say, let's label the diagram according to external momenta, because that's more useful for amplitude calculation. So Feynman diagram is labeled by amplitude. I'm not going to keep track of labeling of the vertices instead, because I'm going to anyway integrate over all of the positions. Okay? And then Feynman rule was invented to be able to compute this, not an operator, but a function. So if you look at this now, this will turn out to be just a function. Already you might say this is a function, not an operator. Okay. So, so this is a scalar propagator, and then fermion propagator. So let me specify charge fluid, and then momenta. So from this definition, if you had a diagram where momentum fluid is reversed, okay, in other words, now momentum goes against the charge fluid, then obviously you have the minus sign from here, okay? And then we had a Yukawa vertex where I had two fermion and then scalar. And then something coming in, something coming out, because there's always one sidebar and the one side, okay? So there's always charge fluid preserved, and this will be denoted as minus G if the vertex has some structure gamma, which I haven't specified, but I probably talked about last time that this gamma, in principle here, can be either 1 or gamma 5. And we talked talked about already that we constructed the 16 bilinears. And then if it is a 1, we show that this is a scalar, so therefore this will be scalar. If it's gamma 5, we show that that's a pseudoscalar, so this should be pseudoscalar. Okay? Anyway, so depending on gamma, that's what you want to have. And finally, suppose I look at some horrendous diagram with many scalars coming up like so. I don't know how many in between, doesn't matter. And suppose I have a charged fluid like so, and if this is my direction of a time. So this process describes some nucleon colliding with some scalar, maybe 2 scalars, and it comes out with a 2 scalar, and another nucleon comes out, right? If you follow the time direction. Note that now the reason why I say it's nucleon once again is the charged fluid same direction as the molecule. Now then, final rules to keep track of initial and final state is once again you go backward in charged fluid. And since it's nucleon, you start out with here, you have a U bar, whatever final momentum. And then you have a lot of contraction, one vertex, another propagator, another vertex, another propagator. You keep doing this. Eventually, you end with a U with a P. Okay, so that's the rule. If I have another thing where things goes backward, so suppose I use the exact same diagram, but suppose now time was the other way around, then, oops. Let me say the other way around. Suppose now you read this diagram backwards. So therefore, this is my initial state, and these are my final state, and I have a scalar colliding with antinucleon, reducing 2 scalar with antinucleon. Okay? Once again, rule is the same. So again, I have to start out with the head of the charged fluid, go backward. Now, therefore, amplitude will be proportional to this. So amplitude will be now, because antinucleon, we'll start out with the V, okay, it's P prime here. And then there's a lot of contraction, a lot of contraction, a lot of contraction, and with a V over P. Okay, so that's the rules. You might say, oh, looks like that's a lot of rules to remember. I don't want to memorize the rules. That's okay. Even if you don't remember the rules, or if you don't want to remember the rules, that's okay. You just suffer just a little bit more. How? Okay, you start out with the heat here, right? And then expand. And then there is a time order of a lot of chains. You know how to write it down in terms of normal ordering according to the Wick's theorem. And there's a lot of contraction. You don't have to read off each of the terms. Compute a lot of 4 integrals. You shrink down to something like this. So each time you can compute that way too. You're very welcome to do so. And this is just mnemonics to save a lot of time doing a lot of integration and blah, blah. Okay? That's all. Later on, once we discuss a path integral, we will learn how to read out the final rules very quickly instead of actually going through this and compute. Yeah, this should be the right rule. We will have a path integral formulation. So this will allow you to read out the final rule much quickly than this practice. Okay. Good. So 2 more things. One is a fermion loop. The other is summing and averaging over spins. Those are the 2 last items for fermions. Okay, so let's skip this. So up until now, we've been only talking about tree diagrams, meaning there's no loops. Okay, and the 2/3 of this semester lecture is about the loop diagrams on the other. Okay, and there are a lot of physical meaning to that and subtleties and technical complications. But anyway, we're going to spend a lot of time with the loops. But already here, let me mention one thing about the fermion loops. So let's consider that theory of fermion loop. It looks like this. Okay, so there's a fermion loop. Let me see. 1, 2, 100 U1. This is enough. Keep attention. You can add a lot of more. I mean, every single point you can just add this, right? So here's a fermion loop. Okay, so there's a 8 scalar points. So if you compute successfully you get something like 5 to the 8. Okay, so what about the fermion loop? So let's label vertex. Let's label. So this is, let me call 1, 2, 3. Oh, is this clever? No, it's not clever at all. 2, we found this. 3, or I mean, the other way is totally fine, but not the most. 7. Okay. So again, if you follow the Week's theorem and blah blah, what you're gonna get? You have to pull down. Well, I have to write. So this e to the minus before x, this thing. Now you're looking at 9th order information, right? So what that means is that, okay, that was a mistake. Just too many. Anyway, it's short. Let's do it. So T of how many? So psi. I think I did a mistake, right? Good. No, totally. So let me take this to be 1 for now, just to suppress some notations. There's 1, 1, 1. You think I'm gonna write all eight of them? No, I'm not gonna write all 8 of them. So psi. So 8, 8, 8. Okay? And what? So this is time ordered. That means that this will have a lot of weak contraction according to Week's theorem. And you can ask which weak contraction corresponds to this diagram. So this diagram says from vertex 1 to 2, there is a fermion propagation. And then that means that 1 to 2, I have to have a contraction. Good. Right? And then 2 to 3, I have a weak contraction. So that means it's a propagation. That means I have to have a 2 to 3, 4 to 3 to 4 exponential first, and then eventually 7 to 8 contraction. And then since once I arrive here by going around the loop, again I have a final propagation from 8 to 1, which means that this has that contraction. Okay, so what I'm saying here is that this will give you a time order thing. And then I'm not saying that, okay, this particular expression should not make any sense to you. This is a mixture of time ordering and the normal ordering. Well, you know what I'm saying, right? So time ordering has a lot of weak contraction, and this is one of the weak contraction that associate with this stuff. That's what I'm saying. Good. Now, so any pair of fermion operator, or otherwise known as fermion bilinear, is a bosonic object. This is bosonic, and then another contraction is bosonic. Also, this is bosonic. Right? Good. Now, in order to bring this fermion and that fermion, which is contracted in a normal sense, meaning sidebar sense, okay, what I have to do is I have to move this guy around a lot, pass all the way to this point. Yes? Okay, so this should be moved all the way up to this point. Now, for a while, it's okay because I'm only passing through the bosonic contractions, right? But the last minute, I have to flip one fermionic thing. But this is universal regardless of number of contractions, number of bosonic lengths here, as you see. Because intermediate, everything is bosonic contractions. So universally, there will be only one of -1 because you have to eventually pass one fermion, and let me just write that as -1 to f. To remember that this comes from that fermionic flip. Good. Then the last thing is that this whole thing can be written as follows. So first of all, this thing, normal contraction, therefore, there's a structure that -1 to the f. And then let's keep track of indices. So I will have now psi 8. And then let me write down spinor index A. This is a 4-component spinor, remember? Okay. And then what do I have? Let's forget about the scalars. And then I have psi bar. Remember that looked like P slash plus M or P slash minus M, depending on U or V, right? Anyway, this is 4x4 matrix, which means that I will have 4x4 matrix multiplication. And then I have another sidebar, which is a B, C, et cetera, a lot of chains. And then eventually, what do I have? Oh, okay, I missed one thing, sorry. Let me start out with the side 1. Just let me follow this thing for now. And then eventually I have side 8 left. So it's D, E, eventually E. Right? And then, sorry, without this. And then I move this guy all the way here. That's what I did. Okay, so I move this guy. Oh. When I do that, I pick up the -1 to the F, and then side A to the E. So if you look at this entire chain, this is like, some matrix EA contracted AB, contracted ABC all the way, and eventually BE. So this is gigantic matrix multiplication. Okay, right. This is also matrix E/1. But then this has a structure of some matrix starting out with an E, a lot of contraction, and end with an E. So that's a trace. Because this is sum. So it means that whenever you have a fermion loop, there's a universal feature that first of all, you're always gonna pick up the -1. That's 1. And B, the chain of a string of fermionic field that you have to compute is eventually trace of stuff. Okay, sidebar, side. Possibly gammas here and there. There's capital gammas here, if you use non-trivial. So for fermion closed loop, you always have -1 side, which is also related to the fermionic statistics, and then eventually it's a trace of the strings. So that's the one comment about closed fermion loop. Okay, question. Yes.
So, like the physical meaning of the closed loop diagram.
Physical meaning of closed loop diagram. Okay, so there are many ways of understanding the fermion. Not just fermion loop, in general loops, which will be the subject in the rest of the course. But just to answer very quickly, one, say, physical way of understanding it. For now, let's just look at the, like, for instance, like their diagram. Okay. One technical meaning is if I want to look at the two scalar scatterings, right? Suppose in addition to all of this term, I just randomly added a lambda 5 to the first. Then if somebody asks you, oh, can you just tell me, scattering amplitude for two scalar goes to two scalar scattering process? And this will include, for instance, as a leading term, just tree-level diagram with this vertex being -I times lambda. And then this will be additional contribution to that, to the scattering amplitude. Because eventually, this is part of some blob. So I don't know what goes into the blob. I just want to see, there's a 2 goes in, 2 comes out. Tell me everything that gives me that connected diagram. And this will contribute to one of those terms. Okay? So this goes like lambda, this goes like -ig to the 4th. But eventually, because of loop, it will have extra suppression. Okay? We will talk about the sum suppression because of the loop structure. So technically, therefore, loop diagram can contribute to physical process amplitude. That's number 1. That's number 2. Physically, whenever you see this sort of diagram, one way to think about that is that suppose I shoot two scalars phi in. Like quantum mechanically, suppose that these are much heavier than scalar. So for the moment, let's consider just to illustrate the point. Suppose let's take the case where size of the fermion mass is much greater than scalar, which means that physically, if you collided two scalars, there's no way you actually excited two fermions because they are much more close. Right? Suppose you just have a two scalar whose mass is much smaller, and then even the kinetic energy is not enough to be able to produce these two fermions on shell, for instance. Okay? Therefore, if you ask the question, okay, can I produce two fermion out of one scalar? On shell, it's not possible. If I consider this particular case. Okay? Now, quantum mechanically, what can happen is that because of this observable principle, if you look at the extremely short period of time, your uncertainty energy can be very, very large. So for a very short period of time, you can borrow a lot of energy from the vacuum. But you have to pay back very quickly. So you cannot borrow that money for a long time. Okay? So you will be caught by quantum police very quickly. So you have to pay back. So what happened here is that, oh, okay, so I'm going to collect this. I know I don't have an ability to produce fermion pair, but vacuum can. Because this vacuum has a lot of money, a lot of energy. So if you cut this diagram, it's like, oh, for the moment, let me produce it by borrowing energy from the vacuum. Okay, violating energy conservation for that small period of time. But I know I can't do it very long, so I have to go back. So therefore, quantum mechanically, like I collide two particles, very short period of time I'm producing some heavy particle, but I have to annihilate very quickly going back. So on the world, it looks like energy is totally conserved, nice and beautiful, blah, blah. Okay, so that's, if you like some physics intuition, you can attach to this sort of loop diagrams. Eventually, we will make this statement very sharp. There's a unitarity state. Are there any questions?
The tracing, it seems very similar to the procedure when we calculate the amplitude scale based with
That's very good. Good. So we will talk about that like right after.
Okay.
Indeed, this is an almost identical structure to that. Okay. Okay. Why don't I go on to that now, and then I will make a one statement, which I found from the Coleman's book, which I found it illuminating, and then we can come back to this and compare. But your observation is absolutely correct.
Yeah. We know about optical theorem.
Yeah. You know, but probably not many people know. Yeah. Yes.
But we deal with quantum.
Yes, everybody therefore should know optical theorem. Yes.
You didn't relevant to this situation too.
Good. So we will eventually talk about unitarity or optical theorem, in a fully general sense in the relativistic scheme, and then you can take a non-relativistic limit to get an expression that you have seen in the quantum mechanics book, and that will be identical. It's not like two separate optical theorem. It is actually the optical theorem. Okay, because even non-relativistic quantum mechanics is unitary. So whatever expression controls the optical theorem expression based on unitary, you should have optical theorem. So that's true. Any other questions? Good. All right. So the last thing is spin cell. So the last thing I want to talk about the fermion is the summing over or average over a spins. So what is the physics context of this? So let's consider the following situation. So here's the big block, meaning something non-trivial happens here, okay? And then I collide, say there's a one fermion, another fermion, if you like, there's another gauge boson, which we'll talk about soon. They collide, and if you like, let's add another scalar just to maximally make it interesting diagram. And then boom, something happened, and then something start coming out. Okay, there's a scalar, two scalar, there's a one gauge boson, something comes out like so. So this side is like what you prepare. Like not you, but experimentalists prepared, right? So this corresponds to proper tables B, for instance, at LHC. So for instance, at LHC, Large Hadron Collider, they prepare a proton and proton. Okay, and they are very good at making protons. So they circulate, they go to the very high energy, at some point they collide. Okay, it looks like a very small beam. If you zoom in, it's like big, gigantic ball of craziness in this side. Okay, there's a lot of stuff in it, they collide. And then this is therefore initial state. And then something comes out. Okay, so this is the final state. And then here, this is the detector. So you detect. Okay. So now the situation is that often, not necessarily every time, we cannot polarize. So we use unpolarized beams. For instance, as I told you, LHC uses the protons, for instance, use fermion protons. And then we cannot, I don't know if we cannot, but at least we don't actually polarize protons. In other words, I don't just collide spin-up protons. Okay, I just make the protons that just collide. So since we don't know, we don't do the polarization of the beams, often what we have to do is that we have a statistical distribution of all the spin states, right? And if I just create a whole bunch of billions of protons, some is up, some is out, down, and so on and so forth. So this here is a statistical. However, some of them, planned machines which hasn't realized yet. Example can be ILC, International Linear Collider. You really want to have one, but we have a hard time having one. So if you're super rich, like $1 billion rich, or $10 billion rich, you make that happen. So anyway, so in that case, we are actually, so this collide electron and positron instead of proton. And then one of the very important strengths of this machine was that we can polarize electron and positron very well. And turns out if you can do that, we can learn parallel physics. Okay, so anyway, some cases, we actually use polarized thing. Okay, but in general, that's not. So in that case, we are talking about statistical distribution of spins. What it means is that when we compute the scattering amplitude, which, okay, for instance, a process like this, we have to average over, because it is statistical spins, average over initial spins. Okay, so suppose I had an in-state fermion with a spin R. That means that I have to do sum over R and then divided by 2, because I'm talking about spin half states. Now, when it comes to the final state, on the other hand, here, often we don't, either can or don't actually detect spin of state. So we usually, especially at LHC, what you do is that you produce a lot of stuff, and then usually you have a calorimeter, which means that you just deposit energy and read out the energy. Okay, sometimes you can read out the trajectory where it comes from too, but most of the time we are recording energy of the state, and we don't quite record a spin of the state. So in that case, what you do is that whenever something happens here, you're basically going to detect everything that happens. So you're going to basically have to sum over all possible spin states. Okay, so for final state, you have to do sum over spins. So for instance, if I had a fermion comes out with a spin S, in this case, you have to do sum over final state spins. But you have to understand under what circumstances you are doing this, okay? And after this lecture, maybe you forgot what was the condition. You always use this formula without thinking anything about it, but it's a simple concept. So you have to keep track of the machine and conditions, and then do the right computation. Okay, so let's do this spin sum. And you remember that cross section super schematically is like square of the amplitude that we were computing, and then there was a whole lot of phase space factor, right? There's a phase space that we discussed. We talked about two-body final state computation and so on and so forth. What I'm saying is that when you compute this matrix element square, you have to factor this in, okay? Average of the initial spin if you're using the unpolarized beam, and then sum over final spin if you don't detect spin of the final state. So let's take the example and then just illustrate the point. Okay, let's consider m plus phi equals m plus 1. Because since we have already done the calculation. So in this case, the matrix element with the spin R and S, so let me label spin according to this labeling was minus IG squared, and then U bar, final state S, P bar, P prime, right? And then let me take gamma equal to 1 for now. E slash U slash minus M, then U, P, R. So that was the amplitude we computed. Okay? So this propagator factor, obviously, as we talked about, can be rewritten as something like this. Forgetting about the epsilon factor for a second. So basically, matrix element with the spin S and R has a structure that either it has like U bar S times number times U R, or it has a structure that there's a some momenta K slash U. So for instance, these two factors will give you an amplitude that looks like this structure, right? And then this factor, for instance, will give you amplitude that has that structure. Okay? And in principle, this can get a little bit more complicated. For instance, if you use the gamma, this is for gamma equal to 1. But if you use the gamma equal to gamma 5, obviously there can be gamma here, gamma there, then means gamma here, gamma there. So in principle, amplitude now also can have gamma, either number 1, gamma square, gamma, K slash, gamma U. So you can think about all possible structures, basically. Okay? Now, this is technically basically the same as this, if you know a couple more identities that I will list. So for now, let's just focus on this. This is pretty easy. So let's just focus on this and talk about how to do the squaring and then how to do the spin sum and average. Okay? And then the rest should be almost identical, technically. Okay, good. So let's just focus on this. So what we want to do is the following. Basically, we want to do the sum over final spin and average over initial spin. And then I want to square this. This is what goes into the calculation of cross-section. And then for now, again, I'm just gonna take the simple form that this is U bar P prime, and then some vector K slash U P R. Okay, to demonstrate how calculation goes. But note that this is not entire amplitude in the particular is a polar. Anyway, so this goes like this. So then this is what? SR dagger. SR, let's first compute this object. So SR dagger is U bar S K slash U P R dagger. Okay, done. Yes, done. So let's do it. So U R P dagger. And then this is gamma mu K mu. So gamma mu dagger. And then remember, this direct adjoint has a U dagger gamma 0. So I have to have gamma 0 first, and then U S, and then K. So far, I literally wrote down what you would get by just doing the Hermitian conjugate. Okay. All right, so because I want to write everything in terms of not U dagger, but U bar, so I'm just going to insert gamma 0 squared, which is 1, according to Clifford argument. And then I know that I've been using the representation where this is Hermitian. So this gives me U bar RP, and then combine the 1 of the gamma, and then I have gamma 0, gamma mu dagger, gamma 0, so that's the rest of it. That's P and mu. Good. And remember, we define not only the direct adjoint for the vector, we also define a Dirac adjoint for the matrix. So for given matrix, in this case 4 by 4, I define the Dirac adjoint as so literally Hermitian adjoint multiplied by gamma 0. This is gamma mu state. Okay? And then this, you can check, is equal to gamma mu, I mentioned before. Okay? But go and check. So at the end of the day, taking the Hermitian conjugate of that particular combination is pretty simple and nice in the sense you literally just, flip order, but taking the same structure. Okay? Good. So then I'm ready to compute that. So let's do it. F of R and S. So simplify. U bar, this diagram was this, K slash S P vector, K slash. Okay, well that's it. Okay, so now here comes the step. Okay, also mentioned by there was one question. So this, if you look at it, is also like trace because this is for let me make sure. Row vector is one row per column. It's 1 by 4, right? And this is gamma mu in it, so it's 4 by 4. And this is 4 by 1. And the same. So this is all just number. Okay? So the point here is that overall the entire thing is a 1 by 1 number. However, so then sum over, so let me make sure. For each choice of R and S, where these two runs 1 and 2, remember, this is a 4-component spinner, but it has two basis vectors, 1 and 2, 1 and 2. 2 for the particle, 2 for the antiparticle. So for any choice of R and S, this is single number. And then sum over number is a number. And then here, this is I learned from Coleman, it was actually Feynman's original idea that 1 by 1 number is the same as a trace of a 1 by 1 number, which is true, right? And Coleman said this saved the generations of physicists computing this. I wish I didn't know because I trained already like that. I just did it. So it's just fun to see. So this is the overall number. Okay, this therefore is the same as trace of number. So this is right there. Okay. You know what? So there's an equal sign, and that arrow extended all the way up. And so, okay, I'm now simplifying my life. Trace. Right? Done. Good. Now, beautiful thing happens. Yeah, beautiful thing happens. So there's all the matrices. And then by cyclicity of the matrix, I can always move around things like so, right? So let me just rearrange this thing, which is 1/2 trace of, okay, let me skip R and S, and U R, so I'm just moving this guy, U R, okay, like 1 by stuff, K slash, and then U S, bar, K slash. Good. Oh. And then we learn this acts as a projection operator or spin sum, whichever way you want to say. This is the prime place. Good. So therefore, this collapses to a simple notation. So this is true after summing over spins, right? That's the spin sum formula we talked about. This becomes P slash plus M, K slash, P prime slash plus M, K slash. So the entire amplitude collapses to that formula. So now you see that amplitude is genuinely a function of just the momentum, nothing else. So this thing includes a couple of structures. And let me just mention quickly and then we're done with it.
트레이스에서 앞으로 바꿀 수 있는 게 매트릭스를 옮길 수 있는 거 아닌가요?
Yeah.
벡터를 옮겨도 되는.
Vectors matrix. N by N matrix. In other words, okay, let me say another different way, if you like. So the question, but first of all, the question was, I just move around this guy. The question is, isn't it that we can move things around if it is a matrix rather than a vector? Okay, and obviously, if I start writing down the spinor indices as I did for fermion loop, every single entries are number. Some of them are C number, committing number. Some of them could be anti-committing number, but number. And number obviously can be exchanged if you keep track of a sign properly. But nevertheless, you can keep track of, you can exchange orders. So given a matrix, so for instance, system expression, suppose I have matrix Ij. Suppose I write it as Kikj. And then if I multiply this matrix, I don't know if this is the best way of talking about. Check. But what I'm saying is that for each entry, these are just numbers. I'm allowed to rearrange the order of it. So long as I keep track of, either committing versus anti-committing number nature, I'm allowed to just reorder it. This is number. And then this is a matrix notation, if you like, of this expression, which a priori is just a chain of numbers. So what I have done is, given a number, I actually can move around. That can be reinterpreted as moving around, in this case, 4 by 1 matrix. That's what I said. Or actually, that's not the best example. Let me just write this. ABC is equal to BCA. Right? Good. And I haven't specified the size of matrices. This is true. Right? And obviously, in order to be able to have a notion of a trace, I should have a proper contractions. K, I, if I write in terms of an index notation. K, I, right? But I haven't told you like J runs from 1 to 2 or 1 to 1 million. Yeah. This is true. That's exactly what happened. Okay, any other questions? Good. So, yeah, so this one has a couple of expressions, I said that matrix element or Feynman amplitude is only a function of external momentum, right? And it was not so clear at this level before. But now it's totally clear. This is 100% a function only of external momentum and obviously mass, primary theory. So in order to be able to compute this thing, it seems like you need to know a couple of things. First of all, like, what is this thing? Because I have, for instance, if I look at the M, this M term from this piece, M from this piece, then it's a K slash X slash. So it looks like I have 2 gamma matrices in it. And then you might say, what about this? Because I can look at P slash K M, K slash. There are 2 gamma, no gamma, 1 gamma. So there's an odd number of gammas. We also need to know this, because now I take P slash K slash P prime slash K slash, 4 gammas. And then in principle, instead of a scalar interaction, if I use a pseudo-scalar interaction, then I told you that I can have a whole bunch of other gamma 5s here and there. If you have done that calculation, here and there will be gamma 5s, right? So you might be wondering, what is gamma 5, gamma mu, gamma 5, gamma mu, gamma nu, all that basically. Gamma 5, gamma nu, gamma no, last thing. Gamma 5, gamma nu, gamma mu, gamma rho, sigma, right? So it's clear that you want to know these identities. So, do I want to write down the answer? Probably no. So, and here also, let's start out with the again. Okay, here is this answer sheet. I'm not giving you the derivation. So I think one of the whole problem from the Coleman's book is actually derive all of that. So go and do it. Once in your life, do it line by line, every single plus minus, and have I. Okay? And then you'll be in comfort. Otherwise, you will ever be scared. Like, okay, I haven't done that. I don't know, but I'm using it again and again, but I never see the derivation. You'll never get rid of this weird feeling. Just do it, honestly. So this is 0. And this, using the Clifford algebra, is same as the other, so it's an infinite. So this will give you 4 times metric. And any odd number is 0 for any convince yourself why that's true. Okay? I mean, you will do a lot of Clifford algebra to switch around stuff. Basically, Clifford algebra combined with the cyclicity will tell you this answer. You have to go several times to do the Clifford algebra, but cyclicity says that that should be equal to that. But if something is minus of that, which is same as that, it's 0. That kind of one. Anyway, in case you got it, congratulations. If not, let's do it. So 4 times eta mu nu, eta sigma mu, this is typical, sigma, well, this is 0. Good. So very happy this is 0, isn't it? 0, aha. Super happy. What about that guy? 0, very satisfying. It's minus 4i, epsilon, and mu. Okay, so you wanna derive this, but then that thing is done basically. So let's do very quickly. So the only non-zero thing is 2 gammas, because I don't have gamma 5, 2 gamma or 4 gamma, no odd gammas, right? So which one has 2 gammas? Well, m, n, and k slash k slash, right? So that gives me m squared trace of k slash the slash, which is basically that thing contract with the 2k mu k nu, which is 4 times k squared. So that's 4 times k squared. Done. And then there's several odd number of gammas, which I don't care. And then I just need to care about 4 gammas. P slash K slash P prime slash P prime. K slash. Good. So 4 times P dot K, P prime dot K, and the minus of P, done. Okay? So that calculation is done. And then you can do the phase space integral to get the process. Okay. I'm done with the fermion, at least for now. I'm gonna move on to gauge fields. Any questions? Okay, so going back to original question, yes, just like a fermion loop here too. I think the same logic is this. So if you have a 1 by 1 number, because of all contractions done and eventually number, you can always replace with trace. So you can discover that either by explicit writing down, component A dot B, and so on, look like this trace, or just by this observation. Okay.
Yes, but I want to know about the physical relation between the one loop.
Oh, that was your question. Oh,
yeah.
Yes. Oh, the physical relation is probably that's what you mentioned. Physical relation is the optical theorem. So this is wrong. Oh, I see. Now I understand. Okay, let me square that. But I have to contract it. Here is your formula. That's why you got the exact same structure.
Okay, then cutting is the optical theorem.
Yes, this is the optical theorem. Okay. By the way, as you may already know, if you type Dirac matrices on Google, It's Wikipedia. You click it, go. All the identities. And there's a proof. Click. You see all the proofs, right? Doesn't matter. Okay, just to follow. And it's okay to follow every single step. But it's fun to check yourself, right? After seeing one proof, oh, I see things work that way. Can I do the next without seeing it? It's all okay, but make sure that you use your brain, not just pen and eye to do it. Okay, so that's all for the fermion for now. Let's move on to the vector field. Questions before we do. Okay, so far we have discussed how to construct consistent field theory, by which I mean Lorentz invariant, and then energy being bounded from below, unitary, blah, blah, field of this, right? So now we have to consider vector field. Okay, you can put indices of it, that doesn't matter, but I want to look at the vector field. But so far the way we approach this sort of question is not necessarily that we classify the possible field. Rather, we classify according to what are the acceptable representation of a Lorentz group. And then we ask, what are the field version of that degree of freedom? And then what is the consistent Lagrange we can write down? Right? So that has been the approach we have been taking. So in other words, we've been taking active viewpoint. Instead of saying, I don't know, let's try to write down, let's guess what this theory tells us about. We say, I want to describe quantum field theory of this state. Okay, and then I'm going to construct a field theory of this. So I know what I'm doing, right? Instead of saying, let's just write down something and then guess what. Okay, so then in order to therefore tackle that sort of question and approach, so let's recall that we talked about representation of Lorentz group. And then we discovered that Lorentz algebra is at least locally SU2 times SU2, right? And then there's a two, basically copy of two SU2s. And then we said, okay, looks like this guy, we already talked about, has a 4 degrees of freedom. And then this thing has a dimension, and this thing has a dimension of 2s1 plus 1, 2s0 plus 2s2 plus 1. I have a 2 separate SU2. And then we guess, okay, there might be several solutions. One is either 3 half comma 0, because this one gives me dimension 1, that gives me dimension 4. Or I can do 1 half, or I can do the other way around. So these are the 3 consistent solutions to this first question of the dimension. Now, since we know that, okay, I have space, let me just move on. Then we impose the reality condition, meaning I want to describe a state which is real under the complex conjugation. Or in terms of representation theory, what I mean was complex conjugation of that thing, I want to be equivalent to the original representation up to similarity transformation. And then we saw that the S1, S2 of star is equivalent to original representation of these two spins are flipped, right? That way. So imposing a reality condition, we found out that the sensible vector field is associated with D of half representation. This is a big review. Okay? And also, you remember that this is also how parity works. So under the parity, also, S1, S2 flips. It means that if you look at the real vector representation, it is also parity invariant representation. I'm not saying that theory will necessarily be parity invariant. All I'm saying is that this, as a package of a state, that is parity invariant. And then lastly, if I only focus on the rotation subgroup of a Lorentz group, you recall that because generator of a rotation is nothing but sum of two sp2 generators of this S1 and S2. This is like angular momentum sum. And you know how to do the angular momentum sum if you have one spin state with a spin S1, another one with a spin S2, right? So now if I focus on half and half, we know that, again, under the rotation, this behaves like three-dimensional representation, otherwise known as spin 1, and the direct sum of spin 0, otherwise known as the scalar. Okay, why am I saying this? Well, let's start again with actually knowing what I have to anticipate, right, before jumping into the formalism. So we're going to construct the Lagrangian and field theory and quantize of this theory. Well, we have to anticipate. Okay, because that thing corresponds to that thing, and this thing has these two degree of freedom inside of it, and they don't mix up under the Lorentz transformation. Okay, they are separate, irreducible representations. So we should expect that if I start writing down Lagrangian for this guy secretly or explicitly, I don't know, it will have both terms in it. But let's keep in mind that and then actually distinguish these two states eventually. Okay, good. So what is our strategy for building a theory of a vector field? Well, similar as before. Let's try to write down the most general Lorentz invariant, real, Hermitian, good, Lagrangian. And then start constraining the coefficient by demanding second principles. That's the strategy. Okay, so therefore we're going to do the following. We want to write down the most general first Lagrangian such that it is radix in field. And remember, the reason was then I get linear equation of motion, which means that I can solve it, which means that this describes the free theory, and then I can quantize it with respect to free theory. And then later we can add extra interactions. So I want to construct a theory that has, at most two derivatives. And then there are a couple of clear requests. So I want to write down the Lorentz invariant theory, obviously, and I want to have a real action so that everything's Hermitian and nice once I quantize, local, and so on and so forth. Okay, so that's the plan. Let's do it. So let's start listing what we can do about it. So first, at zero floater in derivative expansion, because I'm gonna keep everything up to two derivatives. Let's organize things according to the number of derivatives I have in the term. So zero derivative. So I have this guy. Obviously, I cannot just write down one of them, which is not Lorentz invariant, right? Because I'm demanding that this is Lorentz vector. So therefore, I can write down one fraction of those two. Good. So this is one allowed. All. Okay. So the one derivative. In principle, there's only one term that is allowed, which is this. For now, we're not going to include this term in the Lagrangian. Eventually, this can turn up later in the form of gauge fixing and stuff. But for now, if you like, this might be possible, but I'm not going to include it. Second derivative. So there are three candidates. One, mu, mu. So the way indices are contracted is derivative indices contracted, and then field indices are contracted that way. And I would like to comment momentarily. The second, this, and then let me see, mu. So I just wrote down probably all possible contractions I can give them. Now, one very quick comment. So these are equivalent, right? By integration by part, they're equivalent. Since I'm assuming flat space and time with no boundary, so I'm not gonna write that separately because those are equivalent of the surface term, but we don't have a surface. So therefore, basically, I'm just gonna keep the second term. Now, more important comment is the following. So if you look at this, so that may remind you of following structure. So if I write down psi I, phi I. So in other words, looks like I'm writing down a kinetic term for each of the field if I view this new index for the vector field as a field space index. So it's as if I have a form component of the field, and then I'm just gonna write down each of the kinetic term. Okay, what I'm trying to say here. Suppose I only kept this term without this term. Okay? At this point, I wouldn't know whether this is Lorentz index or field space index. Okay, and also Lagrange will be confused too. You might say, oh, you wrote down this. Again, I don't know whether I'm talking about n scalar field or one Lorentz vector field here, right? Naively. In other words, what I'm saying is if I don't add you or give you Lorentz transformation property of this guy, but I'm just gonna drop you this Lagrangian, I will not know which one I'm talking about. Is that clear? So there's a degeneracy. So at this point, I don't know whether this guy actually described 4 separate scalar. So in that case, I'm talking about 1 plus 1 plus 1 plus 1. Or I'm actually talking about 3 plus 1 vector representation in a way that I talked about. As soon as I write down the second term, on the other hand, things changes. Now, this is Lorentz invariant only if now this is not a separate field space indices, but actually is also space-time indices. Okay? So this now selects out that, it better be, it better be this if these were the two possibilities. So therefore, at the very least, I know that these two should coexist. Otherwise, there's this degeneracy issue. Is that clear? Good. Now, there will be further constraint on these two terms, which I will discuss. Okay, so therefore, let's start out with most general Lagrangian consistent with this discussion. So I'm just going to write down Lagrangian, which has A mu, mu. Okay, so I start out with this. So first thing I want to show, and then we will discuss a lot about the problem next time, is that any sensible differential is by this. Okay, so that's I want. So this is my unitary. And then we will start fixing more of this function next time, and then study more properties. But for now, let's just study this. Why this is true. Okay. So here I have to actually use one of the known facts, but we haven't discussed it yet. Okay, so here I'm going to have to use one input that non-perturbatively So propagator in momentum space, propagator, let me just call that to be pi of p squared, has to satisfy the following condition. So if I go to the Euclidean space, by Euclidean I mean this is Euclidean momenta, by which I mean if you had a Lorentzian momenta, then you had this minus p vector squared, right? But then we can go to the Euclidean by flipping this sign, by which I mean we can do this. That's what I mean. And you can do that by saying, instead of p0, let me use I times p0. Then if you square I times p0, you also pick up the minus sign, right? So there is an overall minus sign, and then you can rewrite everything in terms of this object. So therefore, if you Euclidean object, which is pi of p squared, but now Euclidean of minus p, because if you do this calculation, this goes to minus of Euclidean modes. You see that? Okay, we just do this minus sign. Okay, so this thing must satisfy the following property. So in the limit where Euclidean momentum goes to infinity, sorry, not zero, goes to infinity, this is bounded by some number. So this is the math fact, but let me say, what does that actually mean? Okay, some positive one. So first of all, let me say the meaning of this expression. What it means is that as momentum goes to infinity, okay, propagator, which is two-point function, okay, right, two-point function. Two-point function behaves like 1 over pp squared. In other words, this is good, but I cannot have something like 1 over pp to the fourth, for instance. So this, if a propagator has this asymptotic behavior as pp goes to infinity, p squared goes to infinity, this doesn't satisfy this bound, right? So if you just plug in here 1 over p to the fourth, that becomes 1 over p squared. This then the p goes to infinity, that becomes 0. But there's a certain lower bound. So that means that unitarily suggests, I'm not proving you where they come from yet, okay? But I'm telling you the statement that any unitary quantum field theory, unitary theory actually, quantum theory, has to satisfy that the propagator cannot die faster than 1 over p squared as p the momentum goes to infinity. So this is a non-perturbative fact. Okay, we will eventually, will we? So this can be proven by studying what's known as spectral representation. Okay, so for now, let's just take this as an input and see how far we can get with this. So good. So let's just accept this for now. Now let's analyze this theory. So in order to do that, note that this A mu is a 4 vector. This is a 4B vector. And you know from vector calculus, for instance, if you're given a vector, right, you can decompose this into something is divergence free, and then something that is control free, right? In ENA class, probably you have done that decomposition all the time. Therefore, I can do the same here. So I can rewrite as 2 decomposition, like so. So let me see what each of these terms means. So where, by the way, where the P term means this. So this is an analog of a divergence-free part. Okay, and this, if you take another derivative in epsilon, that's 0, manifest. This is like curve-free part. So in curve-free part, what we say, whenever we have this vector, we know that this can be written as somehow gradient of some scalar, right? That's what we used to do in electromagnetism. And this is exact analog of that in 40 cents. Okay? So we say that something that looks like this, which is a curve-free piece, we call longitudinal. Why is that? Because if you go to the Fourier space, that term says that this is proportional to the momentum of a propagation. Right? If you go to the Fourier space, that looks like that. So it's longitudinal. And this, by T suggests, is transverse. Transverse. Because of this property. That's like this property in 3D sense. Okay? Now, good. 예.
그러니까 노시부터 책을 다시 써야 될 것 같아요.
아, 네.
오늘만.
예, 그러면 1분 안에 끝내겠습니다. Okay. So that means we will have a more careful discussion next time. But anyway, so far what I said was we're going to set up a theory of a vector field, but then we already learned something about it. And then in addition to that, I'll finish the proof next time that there's a tight constraint on the relative sign of these two, or even size. According to this comes from unitarity. And then the plan next time is that I'm just going to plug in this action and then study the propagators. And then unless this is satisfied, I will show that something like this will happen. Therefore, theory is ill-defined. Okay, so that's the plan for next time, and then we will move on and continue the discussion. Okay, so that's it for today. And for good reason, we have to stop it. Thanks.